Let's now talk a little bit about phase 2 metabolism. So phase 2 metabolisms are reactions that are conjugation reactions. They're carried out by the enzyme. The conjugating group needs to be activated, typically in the form of a coenzyme, and they consume energy. So the most common transformations that we'll look at in this class involve the transfer of um, glucuronic acid, which is loaded up and pre-activated as UDP, glucuronic acid. So the group that is transferred in slide is in blue, and the activating part is in black. Glutathione doesn't require direct activation. Then we have SAM, which is S-adenosyl methionine, which transfers a methyl group only and utilizes all this complex cofactor to do that. You will be very familiar from biochemistry with acetyl coenzyme A, which serves to transfer um, um, the acetyl group utilizing the coenzyme A as activating groups. And then we have phosphate and sulfate, which are actually sulfate in this case, which is transferred by utilizing this PAPS cofactor. Amino acids are the only exceptions that get transferred directly, and we'll see actually with a slightly different mechanism of action. So this slide is summarizing the conjugate that we obtain, the groups to which it's conjugated, so what kind of group we need on the drug, and the transferase enzyme that does it. So let's go right in and talk about glucuronidation. This is carried out by an enzyme called UDP glucuronyl transferase, and again utilizes these functional groups on the drug and attaches basically this sugar onto the drug, making the drug more soluble. This is at the expense of UDP, and so basically consumes energy by cleaving this highly energetic bond between the glycan and the phosphates. This is a very important enzyme because it turns out that it's one of the main detoxification mechanisms for heme catabolism. And so heme here is oxidized to biliverdin and then to bilirubin. Bilirubin is excreted in bile, and that goes into the GI tract. And basically is eliminated by the GI tract through the intestine. However, one of the intermediates can be reabsorbed by the portal circulation and then end up back into this tract in which it gets destroyed. The important thing to know is that bilirubin is also highly toxic, and the toxicity is especially for newborn. The reason for it is that newborns don't have a very tight barrier yet between the brain and blood circulation, so their brain-blood barrier is not completely effective yet, and so this adduct bilirubin ends up, penetrating into the brain and causing brain damage. It's rather insoluble, and so it's carried by albumin in the bloodstream, and it's also degraded by light, which is why many newborns that have this problem, and so where basically bilirubin accumulates, they appear jaundiced, so they appear slightly yellow in their coloring, and they're treated by light therapy. And so oftentimes they make home with a lamp that the parents then utilize to irradiate the child and help them metabolize bilirubin. This is very important, once again, because if this is not done, then there can be, as a consequence, brain damage. And all newborns are tested for this particular bilirubin accumulation. Okay, what are the sites of glucuronidation? Um, well, those are the hydroxy groups, and once again, glucuronidation also um, contributes to inactivating bilirubin and making it more easy to excrete when it makes it to the bloodstream. And so, in general, all hydroxy groups and you know, amine groups are good sites for glucuronidation. A related compound is a sulfate conjugation, and that happens with a cofactor called PAPS, which contains an activated sulfate linked to a phosphorus, to a phosphate rather, and that's a very high energy bond. So in the presence of PAPS, PAPS transferase basically transfers a sulfate to alcohols and other hydroxy groups, and that's part of the metabolism, for example, for acetaminophen. It's a very um, common for phenols in general. We also can conjugate amino acids such as glycine, glutamine, and other amino acids directly to carboxylic acids. In this case, the mechanism is a little different because the amino acid is not pre-activated like we have seen for all the other groups, but rather is the carboxylic acid that is pre-activated by ATP. So we have the AMP derivative, and that in turn reacts with coenzyme A to form an acyl coenzyme A intermediate, and that reacts with the amino acid. So we have expensive energy in the form of ATP and coenzyme A. These glycine conjugates end up being more soluble than the starting point, and therefore they're eliminated more easily. Another good way of inactivating and metabolizing via phase 2 metabolism is glutathione. Glutathione is a basically main detoxification mechanism for any reactive electrophilic compounds. And so this nucleophile is a sacrificial nucleophile. It protects vital cellular components and acts as a scavenger. The most nucleophilic site is the cysteine. This is a tripeptide, and it's found in most tissues. So after initial conjugation, this is further metabolized. So let's see, for example, what happens when we add glutathione to a reactive epoxide. So first we have glutathione S transferase, which forms the, basically opens up the epoxide ring and forms the first adduct. Then the glutamic acid gets taken out by gamma glutamyl transferase, and then this is followed by cysteine transferase glycinase, which cleaves up the glycine on the other end of cysteine. And then finally, we get acetylated at the N terminus by acetyl coenzyme A, resulting in final derivative, which is the mercapturonic derivative. And so this mechanism can involve several ways. So for example, in the detoxification of methyl parathione, there are two possible pathways. We can either, glutathione can remove the first, the methyl group or the phenyl group, and ends up with two different metabolites. And we see this reactivity as an important detoxification pathway, for example, for chloroaromatic acid. One of the main situations in which we see the protective value of glutathione is in the metabolism of acetaminophen, which is generally a non-toxic drug. It's pretty safe NSAIDs, and it's found in Tylenol, for example. It can be metabolized by several pathways. We can have sulf basically the sulfate adduct. We can have glucon, the UDP, glucuronidase acid metabolite. It can also be oxidized by a cytochrome P3A4, of which the basically people with alcohol abuse problems have elevated levels, and so we end up first forming this hydroxy and hydroxy derivative, and then this is further oxidized to yield a benzoquinone imine metabolite, which is very toxic. The reason this is very toxic is because it's very electrophilic, highly reactive, can react with cellular proteins to form these toxic effects. And so the net effect will be of liver damage. So overdose by acetaminophen can actually lead to liver disruption, and that is lethal, and the only cure for that will be a liver transplant. Luckily, this adduct can be destroyed by glutathione through action of glutathione S transferase and result in non-toxic metabolite. Another important metabolic phase 2 processes is acetylation. So this is the main metabolism for drugs that contain primary amine moieties, and acetyl group is transferred with assistance by acetyl coenzyme A. It doesn't augment water solubility per se, but basically functions to terminate action to kind of cap molecular groups. These metabolites are usually less toxic, but somehow, because they're less soluble, can also precipitate in the kidney, and that's a problem that we'll see particularly with sulfonamides. Okay, so just quickly, these are example of what happens with sulfonamides, which are antibacterial agents, when they're acetylated, and the site of acetylation. And apologies for this quick overview of reactions, but as you can see, reactivity can be very complex. So isoniazide, which is a anti-tubercular agent and is generally very safe, gets acetylated to form this adduct, which again then gets hydrolyzed to isonicotinic acid and acetyl hydrazine, which in turn reacts with other enzymes by cytochrome P450 family, generating oxidative reagents that can form reactive intermediates and therefore cause liver damage. For this reason, there are different effects by isoniazide, which is generally a very safe drug in patients, depending on their ability to acetylate the drug. So people who are poor acetylator are at higher risk for toxicity by isoniazide at the liver level. And the reason for that is that the drug is metabolized very slowly, and so it reaches a concentration that is toxic in the bloodstream and goes basically overshoots our therapeutic window. So the drug is very effective in the population which is fast acetylators, where the drug is effective, stays within the therapeutic window, and does not cause overreaction. And that's true for the vast majority of patients. However, slow acetylators can overshoot the toxic level of the drug in the plasma and therefore experience liver damage. So one important thing to note is that several factors can influence metabolism. Factors that influence metabolism are, for example, age. So we have seen that glucuronidation is fast in adults, and so they can eliminate drugs like chloramphenicol and also bilirubin very easily, whereas newborns have very slow level of this UDP glucuronidase transferase, and therefore um, end up accumulating to toxic levels, chloramphenicol and bilirubin. And so the age of the patient is something that needs to be, you know, considered when deciding the drug, the level, the dosage for a drug. Now, let's look at the next factor that can be influencing the metabolism, and that is the simultaneous assumption of a drug like ketoconazole that can inhibit, for example, cytochrome P3A4, and therefore interfere with the metabolism of this prodrug terfenadine, which is metabolized in vivo to the active form, which is fexofenadine, and thus the antihistaminic level, the antihistaminic product. On the other hand, metabolism can be increased. For example, patients that abuse alcohol or smoke or barbiturate can basically activated the enzyme that metabolizes warfarin, and so reduces it to alcohol. And in these cases, the patients will actually require higher dose of warfarin to maintain the therapeutic windows. So why all this is important? Well, one of the reasons is also that we can modify the structure of a drug to either prevent or utilize metabolism for our purposes. So knowing the metabolism helps us designing in several ways. We can either design hard drugs, so drugs that resist metabolism. We can design soft drugs, so drugs that are slightly toxic or maybe that we only want to have around for a limited amount of time, such as procaine and lidocaine, which are local anesthetics. And so by designing a drug that gets inactivated rapidly, we control the duration of action. Or prodrugs, and so those are drugs that are only effective after metabolism. And we see an example with the antihistaminic agent fexofenadine, which is activated by metabolism from terfenadine. So let's see a couple of examples of that. So this drug, which is inhibits cholesterol absorption, has a weak site, and so can be hydroxylate at a benzoic position here. And by changing the molecule, by both deactivating the aromatic ring and changing this CH2 group to an oxygen here, we are preventing metabolism. Another example is metoprolol, which is a beta blocker, and it's highly metabolized at these two positions, which are sites of hydroxylation. And so what we did is simply here modifying the tail of the molecule by introducing a cyclopropyl ring, which interferes with binding to cytochrome P2D6 and therefore interferes with hydroxylation. And the final example I want to give is this drug, which is a calcium channel blocker, and is highly metabolized by N-demethylation. And to avoid that, we simply, insert the tertiary amine and change it into secondary amine and insert it in a ring system, and therefore increasing the stability to cytochrome P3A4. So with that, we talked about metabolism, and we looked at a few ways in which metabolism can be our friend or our foe, and how we can alter the structure of the drug to keep that into account.